The third question is about the fitted value approach. It is simple because there is only one endogenous regressor here, right? We have only one endogenous regressor and an intercept, and we have a scalar instrumental variable. So let's think about the first question. It is just purely mathematics. Show that, right? So covariance is not zero. Does it, like, it implies variances are not zero, right? That is by Cauchy-Schwarz inequality. Again, because by the Cauchy-Schwarz inequality, we know that covariance x z squared is smaller than variance of x times variance of z. So it's done. If covariance is not zero, then it must be greater than zero. Then this should be greater than zero, so both cannot be zero because variance is always non-negative. So so that means we will need variance x not equals to zero, variance of z not equals to zero. That is implied by the covariance non-zero assumption. Okay, so later we are going to use variance assumption. Part B, define delta, gamma, and epsilon in this way. That means just it is a linear projection of x onto z. Okay, so we want to linearly project x onto z in this way. So then first delta is covariance between x and z divided by variance of z. Let me drop the subscript I here. And gamma is just it matches the mean on both sides, and epsilon is the residual of this linear projection. So then what we have to show? We have to show that epsilon mean is zero and uncorrelated with z. Pretty simple. Expectation of epsilon is expectation of xi minus gamma minus delta expectation z by definition. And here gamma is defined as expectation of x minus, I will just write it this way, delta expectation z, as you know, right? So yeah, it's already written that way. Okay, then it is easy to see that, and minus expectation zi. Then you see it's cancelled out, so should be z 0. Pretty straightforward. Now let's think about independence between uncorrelatedness between z and epsilon, and that becomes expectation of xi minus z times xi minus delta zi, right? So it becomes expectation zi xi. Sorry. Let me think about it. Is it true? Yeah, it's right. Minus. Here I forgot to write gamma. That's the problem. Minus expectation z gamma z minus delta expectation z squared. Okay. This is not simple. Okay. Now what you have to do here is, I realize it is not easy. I want to rewrite covariance between zx and minus delta times variance of zi. Then proof is done, right? The point here is you have to rewrite this part as, so from here, expectation zi xi minus expectation zi xi zi and expectation xi. This much will become covariance, and later delta expectation zi squared minus expectation z squared. We would like to make it this form. So to do that, we have to compensate this much right? This much is canceled out by this guy. So let me rewrite. So I want to remove this here, and if you subtract this, then this much will become covariance. But because you subtracted this, so you have to add it later. And similarly, I'd like to rewrite this into variance of z. So you have to subtract this much, which is added later. And then what I'm going to show here is this term is just canceled out by these guys, right? I think it's pretty simple algebra, so you can check it, it is 0, right? So they will be canceled out if you plug in the forms. So that is not a problem. And then back to this form, once you can write this, then it is also pretty obvious because delta is covariance divided by variance. You should not have two things. So it is automatically 0. So it is 0. And anyhow, the residual of the linear projection is uncorrelated with the projecting variable. And I am going to define x hat, and let's define x hat as xi hat is defined as gamma plus delta zi, okay? And then the original equation can be written as alpha 0 plus beta 0. Xi is replaced by xi hat plus epsilon plus ui. So beta 0 epsilon plus ui. We are going to consider this much as a new error term, okay? So then what else? What's the next thing? So it's denoted as xi here, and show that the new equation 2, second equation, satisfies the exogeneity and the full rank assumption. Exogeneity and full rank assumption, we need to show in this equation, the exogeneity assumption means expectation of xi hat times psi is 0. Okay, to show that it can be written as gamma plus delta z times beta 0 epsilon I plus ui, right? And you can just expand it. Gamma times gamma beta 0 times expectation epsilon plus gamma times expectation u plus delta times beta times expectation zi epsilon I plus delta times expectation zi ui. Okay, so first we proved this is 0, this is 0 in the previous question. Previous part, we know it, we got 0 for these guys, and we have this equals to 0 and this equals to 0 by the assumptions of the question. So we get exogeneity. So in here, this is regressor and this psi is the error term, so they are uncorrelated. That is the exogeneity assumption. Now the full rank assumption. Full rank assumption means variance of xi hat is not 0. Remember, when you have single regressor, it is the full rank assumption. And then variance, let me think about this. Variance of xi hat equals delta squared times variance of z. Okay, Then for this to be non-zero, first we have to have variance of z is not zero, and also delta should not be zero. That is clearly, if those are satisfied, these two are satisfied, then we get full rank assumption. First, we prove this in part A using Cauchy-Schwarz inequality, right? So we know that, and delta is not zero because delta is covariance between x and z divided by variance of z. Anyhow, the denominator should not be zero. Covariance is also non-zero, so also delta is not zero. So all the full rank assumptions are satisfied. Okay. And the last question. So suppose that the instrument z is actually correlated with u. Then the model is misspecified. We believe these assumptions, but actually it is not. It was not true. Derive the misspecification bias in beta 0. So if you follow this idea, then in the end, you are going to get beta. You are identifying beta from this regression model. Okay, so you are going to get beta 0 in this form, like covariance between yi xi hat divided by variance of xi hat. Okay, this will be your beta 0, right? Right. That's the reason why I replaced x with x hat. And then I am going to continue like using if we replace y with this, pretty much the same thing as we did before, and then covariance alpha and x hat will be 0, and we have beta 0 and variance between x hat, plus the problem is covariance psi xi hat divided by variance of xi hat, right? So we just need to calculate this bias term. So covariance between psi xi hat is, we derived it earlier. Let's see. Here we got 0, 0, 0, 0 here, but the problem is from this term. It is not 0 anymore, right? These 0, 0, 0 are still true, right? These assumptions, when we get this equals to 0, this equals 0, this equals 0, we did not use this result. It was just linear projection, okay? So from the previous derivation, we know it is delta times rho. So delta times rho is the numerator, covariance, okay? Right? Here. And now then the denominator, variance of xi, should be calculated. It is, remember, delta square times variance of z, and remember delta squared is what happened? Sorry. Delta takes the form of covariance x and z divided by variance of z squared times variance of z, right? And it is just, it cannot be simplified. Like, oh, by the way, one delta is cancelled out, so you can cancel out one. So then in the end, you get covariance between x and z in the denominator and numerator as rho, right? That is the misspecification bias. I mean, this much.